Okay. Good afternoon, everybody. I'm Claudio Canizares. I'm the Executive Director for the Waterloo Institute for Sustainable Energy. And it's my pleasure to welcome Kevin Josling, a wise public lecturer. He has generally agreed to deliver. Before I introduce our speaker and the topic, let me go through the territorial acknowledgement. The University of Waterloo acknowledges that much of the work takes place in the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. Our main campus is situated in the Haldeman Tract, the land granted to the Six Nations that includes 6 miles of each side of the Grand River. Our active work towards reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within the Office of Indigenous Relationships at Waterloo. Let me introduce our speaker. Kevin Josling is the Canada team lead for customer success and consulting at Computer Modeling Group. He has over 11 years of industry expertise in thermal recovery processes and conventional reservoirs, CO2 storage, and geothermal. Kevin applies his experience with reservoir simulation, subsurface fluid flow dynamics, and advanced wellbore modeling to provide expert consulting and advisory services to the energy industry. He has presented at several conferences and industry events on energy transition topics. He has worked on assisted and supervised several projects, including CO2 storage in saline aquifers, CO2 phase behavior modeling in the wellbore, enhanced geothermal systems, and closed-loop geothermal. He holds a Bachelor of Science in Chemical Engineering from the University of Calgary. Thank you very much, Kevin. The floor is yours.
Thanks, Claudio. So today I'll be presenting on utilizing subsurface simulation modeling for energy transition. And this presentation will talk about CMG and how CMG's technology can be used in this space. So this is a look at the agenda of what we'll be covering today. So I'll just start with a very brief introduction to what CMG is, or Computer Modeling Group. Next, I'll focus on carbon capture and storage modeling using CMG. Then I'll talk about geothermal modeling in CMG. And then the last section, I'll talk about additional energy transition topics, including hydrogen storage, lithium production, and helium production. So what is CMG? So CMG is a modern simulation technology company that make it possible for energy companies as well as research institutes to take advantage of predictive and comparative powers of reservoir simulation in order to increase profits and evaluate new technologies. So this includes increasing revenue, reducing costs, as well as quantifying risks associated with subsurface operations. So what is reservoir simulation? So CMG's expertise lies in reservoir simulation. So we create reservoir simulation software. So first, let's define reservoirs. So reservoirs, we have fluid, such as oil, gas, or water, as well as energy that's trapped in either porous or solid rock under the ground. This can be difficult to extract efficiently or possibly use as a potential storage or disposal site. Reservoir simulation is a computer program that will model the flow of the fluids and energy inside the reservoir. And as a reservoir engineer, our job is to determine and use that software to how best to extract the fluid or energy. And this can be through techniques such as enhanced oil recovery, well placement, operating conditions. Ultimately, what we're trying to do is perform some sort of optimization on the operations, including maximizing the profit for reservoir development, as well as reducing any associated risk. So CMG's expertise, we kind of have two main buckets. The first one would be traditional oil and gas, which is where reservoir engineering kind of stems from. And then the second would be energy transition. So in traditional oil and gas, we would look at conventional oil, enhanced oil recovery, unconventional, so that would be hydraulic fracturing, and then heavy oil and thermal operations, which are quite popular here in Alberta. And then on the energy transition side, which is going to be the focus of this presentation, we can model carbon capture and storage, hydrogen storage and production, geothermal, as well as other emerging energy transition topics. So the first topic I'm going to talk about is going to be carbon capture and storage. So I'll give a brief overview of carbon storage using underground reservoirs for storing CO2, and then I'll talk about how it's modeled within simulation software. So what is CCS and why do we need it? So um, going forward in the industry or in global energy demand, wind, solar, and nuclear, and as well as other renewable sources are all going to be a part of it, but there's not going to be sort of one energy source that solves all of our energy demand. In the short term, demand is still going to be quite high, and the oil and gas industry is going to play a key part. But as we transition sort of away from maybe oil and gas and into more carbon-friendly energy sources, we need a shorter term solution. And reducing our emissions, and CCS is one of those potential technologies. So CCS is taking carbon dioxide and then injecting it into underground reservoirs for the purpose of disposal and storage. So there are different types of CO2 storage reservoirs located deep within the earth. And the two main types that are looked at today are saline aquifers and depleted gas reservoirs. So a saline aquifer is a reservoir that contains mostly water or 100% water. And then the depleted gas reservoirs are formerly contained hydrocarbons such as natural gas that have been produced and then now can be used to store the CO2 safely within the ground so that it doesn't go into the atmosphere. In terms of storage efficiency, saline aquifers tend to have a larger capacity, but they also come with a higher degree of uncertainty. With depleted gas reservoirs, usually the storage efficiency is less, but there's also less uncertainty. Because we've produced from these reservoirs, then generally the properties are well understood, whereas from aquifers, they tend to be quite large with not a lot of data available for them. In terms of trapping mechanisms, there's different physics that are going to happen when we inject CO2 into these reservoirs. We'll talk about those in the subsequent slides, particularly as they relate to saline aquifers, as there's multiple mechanisms involved. On depleted gas reservoirs, they tend to be less important because there's less water in those reservoirs. In terms of injectivity or our ability to actually get the CO2 into these reservoirs, for aquifers, it's low to medium because these aquifers are at high pressure. It's harder to actually inject the CO2 into them. For depleted gas reservoirs, normally we have pretty good injectivity due to the low pressure of the reservoirs. In terms of wellbore dynamics, on the saline aquifer side, the CO2 tends to stay in the liquid phase or the dense supercritical phase. So we don't expect to see much of a phase change or any phase change happening during their injection operations. Whereas in the depleted gas reservoirs, this is where we could potentially get into two-phase flow happening within the wellbore. In terms of long-term storage and containment, one of the big risks with the saline aquifers is making sure that the CO2 is actually remaining into the aquifer after we inject. And a big one is going to be our fracture pressure and the cap rock integrity. For depleted gas reservoirs, this tends to be less of a concern since we have a lower pressure initially, so we tend not to be injecting up to pressures that will reach our fracturing pressure. So let's discuss some of the trapping mechanisms involved in CCS. So the first one, which is present right from the start of injection, would be structural trapping. So structural trapping is how the reservoir is contained, so how it is sealed. So in the image on the top right here, we can see we have an aquifer that's filled with water, and we're injecting CO2. And then the gray sort of rock would act as the seal. So preventing the CO2 from migrating into other parts of the Earth. We could also have a seal on the side, which might be in the form of a fault, which can contain the CO2 within the storage site. Next, we have residual gas trapping or hysteresis. So this is particularly prevalent when we have two-phase flow. So we have the liquid water phase that's present, and then we have the gaseous or supercritical CO2 phase that will be injected. And the flow behavior or characteristics of the CO2 will be different if the CO2 is displacing water than if water is displacing CO2. So this becomes important when we inject, the CO2 is typically displacing water. And then after we stop injecting, the water will actually imbibe back to where the CO2 is. And some of that CO2 will become trapped in the smaller pores. We also have solubility trapping. So solubility is where the CO2 is dissolving into the water. So when we inject at high pressures, some of that CO2 will dissolve into the liquid phase. So the dissolution will depend on temperature, pressure, as well as the in situ salt content. Once it dissolves in the water, the CO2 can split into its ionic constituents and then actually form different ions depending on the ions that are present in the water. When CO2 dissolves into water, it actually increases the density of water, and this can create a density-driven flow where the heavier sort of CO2 water mixture will actually drain away from the top of our reservoir. Lastly, we have mineral trapping, which happens in the long term. So once the CO2 dissolves into the water and then it forms ions such as HCO3, it can react with some metal ions that might be present in the water, forming and precipitating minerals such as calcite. And this is sort of the safest form of trapping because the CO2 is essentially trapped in a solid phase, but it also takes the longest to actually develop. So this is a look at a timeline scale. So this is actually a log scale as I go from left to right of the different structural trap or of the different trapping mechanisms. So the dark blue would be structural trapping, which is present right from the beginning, and that's how most of the CO2 is going to be contained. As we progress through time, then residual trapping will become more important, particularly once we stop injecting. Then we have dissolution trapping, which is where the CO2 is dissolving in the water. That's fairly consistent throughout the life. And lastly, we have mineral trapping, which will become important, after 100 years of the CO2 sitting within the reservoir. The phase behavior of CO2 is also critical to understand and model appropriately. This is a pressure temperature diagram for CO2. So on the y-axis, we have pressure, and then on the x-axis, we have temperature. The solid line represents the saturation line. And to the left of the saturation line, we're in the liquid phase, and then to the right of the saturation line, we're in the vapor phase. And then the red dot here is the critical point for CO2, which is around 31 degrees and 7 MPa. And then above the critical point, we would be in the supercritical region. This dashed line sort of represents a difference in the supercritical region to like higher density supercritical fluid and then lower density supercritical fluid. When we're injecting at surface conditions, we tend to be close to around 5 degrees Celsius and 5 to 6 MPa. So we would be in the liquid phase, but near the saturation line. When injecting into aquifers, they tend to be higher pressures and relatively lower temperatures. So if we were to go from the injection point to the downhole aquifer, we tend to stay to the left of this line, meaning we're mostly in the dense phase. For depleted gas reservoirs, depending on the depth, they tend to be higher temperatures as well as lower pressures because they have already been depleted. We've produced the hydrocarbon gas from them. So when we inject into them, there's risk that we'll cross over this saturation line and execute a phase change. What are some of the operational risks associated with CO2 storage? We have geological concerns. So from the geological standpoint, it's the plume growth, which is really where the CO2 is traveling within the reservoir. And this is typically the most important that we want to track. This is dictated by the Darcy flow within the porous medium. It'll be influenced by diffusion and dispersion, as well as the density-driven flow mentioned earlier. Where the CO2 travels is going to be based on the heterogeneity or the reservoir properties of the aquifer, so things like our porosity and permeability. From a geochemical standpoint, when we inject gases at high pressures, we can potentially vaporize water near the wellbore. And if we have a high Na plus or Cl minus concentration, this can lead to salt precipitation directly around the wellbore, which can reduce our injectivity. When CO2 dissolves in water, it also forms carbonic acid, which can result in the dissolution of reservoir rock. That can actually help in the long term as well, because that might release some ions, such as calcium, which will then form minerals in the long term. In terms of geomechanical risks, the main ones that we're looking at is caprock integrity. So is the CO2 remaining in the reservoir, or are we creating fractures that will cause a leakage? Thermal fracturing, so because we're injecting CO2 at a colder temperature compared to the reservoir, there can be contracting happening in the reservoir rock, which might lead to fractures. Fault reactivation, so if we are injecting, we're changing the pressure, so our in situ stresses are changing, which might lead to a reactivation of sealing faults, which could lead to potential leakage of CO2. And then because we're injecting into the reservoir and not producing from these reservoirs, we might also have surface heave if close enough to the surface. In terms of wellbore, casing integrity is going to be important. We don't want the CO2 to leak through a damaged casing. Phase behavior, as mentioned earlier, injectivity, Joule-Thomson effect that can occur when we have a very rapid pressure drop over a short distance, so usually over a valve or the wellbore perforations. And potential hydrates formation as well is a concern. So I have an example here using CMG's reservoir simulation that demonstrates CCS. So this is an aquifer, and in this aquifer, it's a relatively low permeability for an aquifer, only 70 millidarcies. The porosity is around 14%, so the rest would be, so 14% of this reservoir is water, the rest would be rock. The depth is 1900 meters, initial pressure 20 MPa, and the temperature is 50 degrees. We have 3 injection wells, so there's the Emerald well, the Jasper well, and the Amethyst well, and they'll be injecting CO2 continuously for 10 years, and then we'll monitor what happens for the next 190 years or 200 years. So this is a video that's going to show the injection of the CO2 and monitoring of the plumes. So the blue area, where right now it's all showing blue, is where the water is. So this is the aquifer, so right now it's 100% water. And the property that we're looking at here is going to be the global mole fraction of CO2. So wherever there's going to be red is where the CO2 is coming. So I'll just play the video. And you can see where the plumes start to develop in the 3 wells. And that's where the CO2 is traveling. Initially, you can see that the plumes are growing very fast. And that's that first 10 years of injection. But then after we stop injecting, we can still see the CO2 migrate throughout the reservoir. Now, the shapes of these plumes are different for each of the wells, and that's going to depend on the localized reservoir properties. So for example, the Emerald well, it's kind of an elongated shape because it's found a channel where the flow properties are more conducive for the CO2. We can also track the different trapping mechanisms that I mentioned earlier. So those are plotted on this screen. So the first one is supercritical CO2. So the purple line here where my mouse is. So when we inject initially, most of the CO2 is in the supercritical phase. There is no CO2 in the gas or liquid phase initially. The green line represents the amount trapped due to hysteresis. And we can see that it increases, but then there's a sort of elbow bend in the amount that is trapped. And that happens after we stop injecting, because as the CO2 migrates away from the well, the water is replacing it. So that's why more of it is now becoming trapped. The blue lines represent how much has been dissolved in the water phase and how much has been converted into aqueous ions as well. And finally, the black line represents the amount trapped in minerals. It's actually quite a bit less compared to the other trapping mechanisms. So I plotted it on a different scale. So the other plots are on the Y1 axis, whereas the black line is on the Y2 axis. And we can see initially the amount of minerals is actually dropping. That's because the carbonic acid is dissolving some of the minerals initially. But then once we have enough ions present, the CO2 will start to precipitate into different minerals. This is a look at a side view. So we're looking at it from the side of the CO2 plume. And we're looking at the impact of different trapping mechanisms. So in the top left is if we only include structural trapping as a trapping mechanism, this is kind of the shape or where the plume would travel to. So the well is not on the screen, but if you can imagine it going up and down on the screen, so a vertical well, and then the CO2 kind of where it is traveling to. If we go down to the bottom left, this is if we include that gas trapping or hysteresis in terms of the fluid flow. We can see at the top part of the plume, it's very similar to the image in the top left, but in the bottom part of the plume, it's actually a lot more restricted, and that's because more of the CO2 is actually getting trapped in the pore space. If we include solubility, we can see the impact that solubility is having. We can see more of the CO2 is actually traveling towards the bottom of the reservoir due to that density effect. So the CO2 dissolves in the water, creating a heavier liquid, which then will drain towards the bottom. And then lastly, the inclusion of mineralization. At first glance, it looks pretty similar to the case in the top right, but if you look at the edges of the plume, we can notice a difference in terms of where that CO2 is actually ending up in the reservoir. We mentioned a few risks, and we can talk about them in these slides here. So one is going to be well placement. So we have three wells. We have the Emerald well, the Jasper well, and the Amethyst well. So the Emerald well, some risks associated with this well is that the same amount of volume has been injected in each of these three wells, but we can see that the plume has traveled a lot further within the Emerald well compared to the other two wells. So there's a greater risk associated with this well that the CO2 could be traveling to maybe outside of our lease boundary where we have a permit to actually inject the CO2, or it could maybe start to interact with other reservoirs if it's well connected. The Jasper well is located near a fault. It's kind of hard to see, but I'll show it in the next slide. Which could be a risk if we thought this fault was a sealing fault. We could be reactivating that fault, and where we thought we had containment, now we're starting to see it leak across that boundary. So the Amethyst well is a little bit safer. We can see most of the CO2 is kind of contained around that particular well. This slide shows the impact of fault reactivation. So we're looking at the Jasper well, which is located near a fault, which is where my pointer is right here. And as we inject, in the case in the top left, we have a sealing fault that doesn't get reactivated. So the CO2 always remains to the right of the fault. Whereas the case in the bottom left, we can see that the CO2 is actually starting to leak across the fault, creating a containment risk. So that was a bit on CO2 and how we can, or CO2 storage, and how we can use simulation to monitor the plume growth as well as mitigate the risks. Next, I'm going to talk a little bit about geothermal energy and how CMG is used in geothermal space. So what is geothermal energy? So it is the energy that is inside the earth, and it's naturally occurring source of renewable energy. Magma will come close to the Earth's surface near where we have tectonic plate boundaries. And then rock and water can absorb heat from that magma. And then in suitable regions, the temperature of the rock or water is hot enough that we can actually generate energy from that. So there's different types of subsurface geothermal resources, which I'll talk about in this next two slides. So the first one is conventional, or sometimes referred to as hydrothermal. In this one, the reservoir behaves very similar to an oil and gas reservoir or an aquifer, where we have some pore space or permeability present. And that permeability and porosity is filled with water. But that water is hot or it's heated up by a nearby heat source. We can then drill a well that we will produce that hot water from. And then if we wanted to continue to produce from that reservoir, we typically would have to inject in order to maintain the pressure. These types of geothermal reservoirs tend to be mostly naturally fractured. So natural fractures is where most of the fluid would flow through. Next, we have EGS or enhanced geothermal systems. In these systems, the hot rock basically has little to no permeability. So there's no fluid initially present in the rock. It's just a hot rock, solid rock. So we need to create a flow path for fluid to flow through. So we do that by hydraulically fracturing. So we inject large volumes of water and crack the rock to create flow pathways. We'll then inject cold water into the fractures that we've created. It'll get heated up by the reservoir rock, and then we'll produce back through the producer wells. Next, we have closed loop geothermal systems. So for closed loop, there's going to be no interaction between the fluid and the reservoir. So these can be used in both permeable or non-permeable reservoirs. But essentially, the fluid is always contained within the well. So there's different types of closed loop. We can have a U shape, which is shown here in the upper image, where we'll inject fluid down one side of the well. We might have a horizontal component, which is where the fluid will get heated up, and then we'll produce back through the producer side of the well. But this is one continuous system where the fluid is not flowing inside the reservoir. Another example would be a vertical well, where we're injecting cold fluid in the annular space and then producing back through a tubing well. Essentially, what these closed loop systems behave like is large heat exchangers, where we're just circulating fluid that's getting heated up through conduction. Some other lesser used geothermal sources, one would be heavy oil late life energy recovery. So in thermal oil and gas recovery methods, so some oil and gas reservoirs require a lot of heat to actually extract the oil, with Alberta being a prime example. We're injecting steam or large amounts of energy in order to extract the oil. And then after the reservoir has been depleted, there's still that energy that's left over in the reservoir. So we can extract that heat and energy rather than just leaving it in the ground. Another one is CO2 geothermal, so combining the impact of CO2 storage with geothermal. So if we have a hot aquifer, we can produce from that aquifer, and then which also helps to deplete the pressure, and then inject CO2 into the same aquifer. CO2 is also used as a fluid quite often in closed loop geothermal systems as well. So some of the physics involved in geothermal reservoirs, we have fluid flow in porous media. So generally, it's going to be naturally fractured, but not all the time. And then we have hydraulic fractures, which would be in the case of enhanced geothermal systems.
Evimde tak tekfir yani.
We also have heat transfer, which will be in the form of conduction, convection, and
Excuse me,
dispersion. And then we have wellbore heat loss and pressure drop. So the wellbore conduction and convection
Kevin.
for temperature drop.
This is Claudio. Sorry for the interruption. There are open mics here, so I'm just gonna ask the colleagues to please turn your mics off. Okay. Sorry about that. Thank you.
Okay.
Go ahead.
Thanks, Claudio. Yeah. Continuing on, so about the wellbore heat loss. So for geothermal, one of the key elements in modeling is to make sure that we're also modeling the wellbore fluid flow and not just the reservoir fluid flow. From geomechanics, similar to CO2 storage, caprock integrity and thermal fracturing will be important, and as well as potential geochemistry and reactions that might occur. In terms of simulation, some of the objectives that we try to get from geothermal simulation would be to maximize the output energy or power. So this would include wellbore completion design, so the size of the wellbore, the length of the wellbore, what kind of completion system. Injection rate and temperature. So what temperature are we injecting into the reservoir, as well as how fast? The faster we inject, the less it will actually heat up. So it'll be less efficient. But then if we inject more fluid, then we're putting more, potentially more heat through. So we have to balance that. Delivery temperature and flow rate, thermal breakthrough. So in the case of open loop, where we have an injector and producer, because we're injecting a cold fluid, eventually that cold fluid will reach our producer well. So we want to make sure we optimize that breakthrough time, which is kind of leads to the third point. So a lot of times we want the lifetime of these geothermal reservoirs to last a specific time, where we're producing a specific temperature or enthalpy before we get that thermal breakthrough. So this is where we can perform sensitivities on well spacing, as well as configuration. In terms of uncertainty, so some of the properties that are often unknown and need to be varied to see their impact on the results. So in terms of the geological formation, we have the thermal properties, so things like our heat capacity and conductivity, formation temperature, and thermal gradient. Geomechanical properties, and whether we have natural or induced fractures. In terms of fluids, we have potential geochemistry, so things with harmful gases, water solubility, as well as scale deposition, particularly if that happens within the wellbore. And then what working fluid we're using. So the two main fluids used in geothermal tend to be water or CO2. Operationally, the things that we would run sensitivities on using the simulation would include injection rate, producer pressure, lengths of the wells, well depth, well spacing, as well as insulation properties. In terms of fluid behavior, certain geothermal reservoirs are hot enough that we could be getting into a supercritical region for water and steam. So this diagram here is similar to the one I showed previously for CO2, but this is for water. So again, on the left, we have, or on the y-axis, we have pressure, and on the x-axis, we have temperature. And then we have the saturation line here, shown by the triangles, and then that transitions into the supercritical region. So in STARS, which is CMG's thermal simulator, we have improved and added in functionality related to capturing the supercritical properties of steam and water. It's also going to be important to look at the enthalpy behavior. So this diagram here is pressure versus enthalpy for water. So the blue line here would represent the saturated liquid line, and then the red line would represent the saturated vapor. And inside the red and blue line, we have our two-phase region, which is where we would have saturated steam. To the left, we would have liquid water, and to the right, we have steam or a superheated steam. So a typical flow path that might occur in a geothermal reservoir is that at the surface, we're injecting cold water at a relatively low pressure. The pressure is increasing due to gravity effects, so the weight of the water, but we're not seeing much temperature change until we get into the reservoir. Once we're in the reservoir, the fluid, maybe we're flowing through the reservoir or through a horizontal portion of the well. We would see the well heat up with minimal pressure loss, just pressure loss due to friction, depending on the rate that we're flowing at. But we're seeing an energy gain, which can be in the form of either an increase in temperature or a phase change if we're near the two-phase region. And then once we're at the sort of producer downhole location, producing back to the top hole, we'll see a slight loss in enthalpy. And so that loss in enthalpy is less than what we have gained because of if we're using insulation. But understanding these, this diagram is critical for geothermal to understand what phases that we're going to be in and what expected energy we'll produce. As mentioned earlier, in addition to modeling the reservoir, it's critical to model the wellbore. In CMG, we have two different wellbore models. We have the semi-analytical model as well as FlexWell. The semi-analytical model is good for simpler cases where we just maybe have a single tubing and we want to know the thermal temperature, the temperature change from top hole to downhole or vice versa. But if we have complex wellbore configuration, so maybe we have multilateral wells where we have a single vertical well that then branches into multiple horizontal wells, or we have multiple tubings. We have those U-shaped wells, so complex well configurations. We can use FlexWell, which is a mechanistic dynamic model. So we have a few geothermal examples here that I'd like to go through. The first one is a conventional geothermal system. So in this one, the reservoir has some permeability. So we're flowing fluid through the reservoir to gain heat. We have 7 producers, which are highlighted by the green squares or the green rectangles, and then 2 cold water injectors, which are highlighted by the blue squares. In the top right, we have a plot of energy rate versus time. And the blue line represents the energy rate when we don't include the injectors in the simulation. So we can see that we can get maybe seven-ish years of meeting our target rates before we lose pressure in the reservoir and we're no longer able to meet those rates. In the red case, though, we've included injectors where we're able to extend the life of this geothermal reservoir to meet those same target energy rates by another, say, 3, maybe 4 years. This is shown here in the average pressure. So the blue line, obviously the average pressure of the reservoir is dropping more, whereas in the red line, we're not dropping the pressure as much because we have that injection, we're able to maintain the pressure. This is another example. This is an example of an enhanced geothermal system. So in this case, we have 2 horizontal wells that go from left to right on your screen. So we have the injector well in the top and the producer well in the bottom. These wells are connected by hydraulic fractures, which might be hard to see on the screen, but they're the thin black lines that run vertically. So these are the fractures that the fluid is going to flow through. We're looking at the property temperature here. So red would be where the temperature is hot, or the initial temperature of the reservoir. In this case, it's 130 degrees Celsius. And then the other colors, like as we get closer to blue, so the greens and yellows, would be where it's cooled off due to injection. So we're injecting that colder fluid, which is cooling off part of the reservoir, but then that fluid will get heated up as it flows towards the producer. In the top right, we have a few different properties. So we have temperature, enthalpy, and pressure plotted versus time. If we look at the enthalpy plot, we can see that it is relatively flat for the first number of years before it starts to decline. And that's when we start to lose some energy in the system because the colder fluid is making its way towards the producer. We can look at the temperature profile. in the temperature profile in between the injector and producer. So on the y-axis, we have distance, and on the x-axis, we have temperature. Injector is located at the top, the producer is at the bottom. At time zero, initially we're at the initial reservoir temperature, which is 130 degrees. But then as we get 10 and 20 years out, we can see that the temperature is dropping as we get closer, or is dropping near the injector, and it's making that lower temperature is making its way to the producer. The next example is a closed loop geothermal example of a single vertical well. And in this single vertical well, we're injecting water through the annulus and then producing back through a tubing well. I have a profile plot here where on the y-axis we have distance or vertical depth as we go down, and then we have temperature on the x-axis. And we have two different scenarios. I have the blue scenario and the red scenario. In the blue scenario and red scenario, I'm injecting through the annulus in both cases, except in the blue scenario, I have tubing with insulation, and in the red scenario, I have tubing without insulation. So in the blue scenario, where we have tubing with insulation, the fluid is going to follow along this line here where my mouse is going, and it reaches a temperature of 80 degrees. In the red scenario, we reach a temperature of 110. So without insulation, we actually reach a higher temperature downhole. But then when we go to produce back through the insulated tubing, the one with insulation, we see very minimal temperature loss. We get to about 75 degrees at the surface. Whereas the tubing with no insulation, we get to a much lower temperature, closer to 60 degrees Celsius. This is another example. In this one, we're looking at closed loop geothermal. And in this one, they have three sort of U-shaped wells where we have an injection side and a production side. Fluid will flow on the injection side down into the horizontal portion and then back up through the producer. And three different spacings were evaluated. So we have 20-meter spacing between these different U-shaped wells, 40-meter spacing, and then 60-meter spacing. This is a look at the temperature profile between the injector and producer at a particular point in time. At the 20-meter spacing, the wells are located too close together, and we're starting to see a drop in efficiency, and we're no longer getting the high temperatures producing them back. But in the 40 and 60-meter spacing, we're able to get similar temperature returns on the producer side. So we would have to balance sort of the closer we drill the wells together, the less efficient they will be. But the farther apart we drill them, we could be having energy left behind. So the last section that I wanted to talk about is just some additional energy transition topics. So these ones will just have a couple of slides on each of them. The first one is going to be hydrogen storage. So hydrogen storage, we can get energy from renewables and then convert that into hydrogen. And then if that energy isn't needed, we can take that hydrogen and actually inject it into an underground reservoir. So that could be an aquifer or depleted gas reservoir. Then we can produce the hydrogen back and then convert it into usable, consumable energy. A lot of the principles in modeling hydrogen storage are very similar to modeling CO2 storage. We have things like solubility, gas trapping that we need to include, as well as geochemical reactions, so things like mineral dissolution. One of the big reactions, though, that's different and that we need to include when modeling hydrogen storage is the biomethanation reaction, which is where hydrogen will react with CO2 within the aqueous phase, forming methane. This is an example of a hydrogen storage case. So in this case, when we have a surplus of H2, we will inject it in the summertime. And then during the wintertime, when we need that energy, we'll produce back the hydrogen. So I just have a short video here. And if we look in the bottom right-hand corner, the green line would represent the gas production rate, and then the red line would represent the gas injection rate. So initially we produce from the reservoir. So this may have been a hydrocarbon reservoir. So we probably produced some natural gas from it. The reservoir is now depleted and we want to use it for hydrogen storage. So now we're injecting for a period of time, a certain amount of hydrogen. Then we produce back that hydrogen in the wintertime and then inject the hydrogen again. The case on the plot in the bottom left is showing the total amount injected and the total amount produced of hydrogen, whereas the blue line is showing how much hydrogen is sort of lost to the reservoir. Next, I want to talk about lithium production and extraction. So lithium is the demand for lithium is becoming quite high as it's used in batteries of a lot of electric vehicles. And so there's different sources of lithium. So we have ore deposits as well as in brines. And then within brines, we have the underground brines, which we can produce similar to producing from oil and gas reservoirs. So there's different types of underground brine reservoirs. We have geothermal reservoirs. So this would be aquifers where we can not only obtain lithium ion that has actually dissolved within the aqueous phase, but we can also use the energy because it's produced at a certain temperature. We have oil field aquifers. So these are aquifers that are connected to oil reservoirs and are supporting them. And then we have standalone brine aquifers. So these would be the ones that would be modeled by CMG. So some of the physics that are involved in the modeling would include hydrothermal alteration or thermal support. So what is the energy transfer that's happening? Reservoir heterogeneities, mineral deposition, any changes to porosity, fluid alteration due to reactions with the rock, complex geology, and subsidence. Oops. The next slide, I have a simple example of a lithium extraction. So this would be a brine reservoir. And in that reservoir, initially, we have a certain amount of lithium ion that's dissolved and contained within the aqueous phase or the water phase. And we want to produce that. But if we produce it too quickly because it's a water reservoir, water is fairly incompressible, the pressure will drop very quickly and we won't be able to produce much. So in this case, we're going to support it with an injector. So we'll be injecting water that doesn't have any lithium and then producing water that has lithium. The property being shown here is the molality or how much lithium we have dissolved. So red would be the highest concentration. And then as I play the video, we can see we're injecting the cold water or the water without lithium in order to sweep out the reservoir, essentially replacing the reservoir fluid without lithium and producing the fluid that has the lithium. The last topic I want to touch on is helium production. So helium is a naturally occurring gas. It is typically generated from the decay of uranium and thorium within the Earth's core, and then it gets trapped in dry gas reservoirs. There's a lot of uses for helium within society. The helium typically is stored in underground gas reservoirs, but it's usually a very small portion. So it's usually part of a reservoir that contains other molecules such as methane. So usually we look for reservoirs that have a certain percentage of them containing helium for it to be economical. Some of the physics involved in helium production, one is going to be relative permeability. This will be important if we have a water phase or water connected to the gas reservoir. We can model gas solubility. For helium, it's usually quite low, especially compared to CO2, which we talked about earlier. Potentially H2O vaporization or reactions. I mean, helium is a noble gas, so it won't react. One of the key ones that would need to be included is diffusion, particularly within the gas phase. So the diffusion coefficient of helium tends to be quite high compared to other gases. So if we have a concentration difference within our reservoir, then diffusion will also play an important role in the flow and not just the Darcy flow. So some of the things that we can get out of a helium production simulation is we can determine the in-place volumes, which will be a key parameter in matching production. We can match compositions, so determine where the produced gas is coming from, particularly if we're producing from multiple zones. So this example on the right, I have a well that's drilled into two different zones that are separated by this white space, which might be like dry rock, so there's nothing there. And then the composition within each of those zones could be different. And then we only know what we're producing at surface, so we would be able to track where most of the helium is being produced from. We can forecast the ultimate recovery as well as optimize the recovery. We can optimize completion design, which will be important for helium production, in particular as it relates to the last point, which is avoiding water breakthrough. So we're designing these wells to basically produce gas, which is very light, so we have no lifting problems getting it out of the reservoir. However, if we have water coning, which is shown in the image in the bottom right, where the gas reservoir is supported by a water zone, that water could come into our wellbore, and the water could be difficult because it's so much heavier than the gas to produce. And so we might change our completion strategy to avoid producing that water. So we covered a lot over the last 45 minutes, so I just want to go over a few concluding points. So understanding and optimizing low carbon solutions are essential for meeting the global energy demand, while also trying to meet our emission reduction targets. Reservoir simulation can be used to reduce operating costs and minimize risks when it comes to CCS projects. And simulation can handle all of the physics associated with geothermal reservoir modeling, leading to the optimal use of the resources. And understanding the subsurface through simulation is critical for developing emerging energy transition technologies. So with that, thank you very much for your attention, and now open to any questions you might have.
Thank you very much, Kevin. I appreciate it. A very interesting presentation. I learned quite a bit. I'm going to open the floor for questioning, but I wanted to ask you a couple of questions first. I, I'm, I'm, I have passing familiarity with CCS and geothermal, part of projects I've been involved in. The first question I have is regarding the accuracy of the models. I'm a modeler myself for power grids. And I mean, depends on the level of modeling, you can be precise and depends on how you apply it. So can you comment on that? How good your models are and whether they vary depending on the application?
Yeah, so the accuracy will depend on a couple of things. So one, it'll depend on the input data that's available. So in some cases, when we don't have input data available, then we have to make assumptions. So in those cases, we will run sensitivities on the parameters that maybe we don't know, so that we can get a range of uncertainty. In terms of the accuracy, though, like if we have something to kind of anchor the simulation to and validate it against. So in the case of geothermal, we've done history matches where we've matched the actual historical temperature profiles as well as energy production. And so through that, then we will have greater confidence in the reliability of the simulation if it's been history matched.
Thank you. And I have another question before I open the floor, which is regarding the cost of geothermal. You had 3 slides in which you were discussing 3 options: geothermal, enhanced geothermal, and closed loop, right?
Mm-hmm.
Could you comment on the cost of this?
Okay. So
Yes.
the conventional enhanced geothermal and closed loop. So the cost, like in the actual field, you mean?
Yeah, for applications, for example, like I don't know, storage of heat or that type of application? What would be the difference in terms of cost? I mean, what would be more costly or depends on the
Right,
resource?
yeah. So what would be more cost effective and everything? So
Correct.
um, it could kind of depend on the type of source, but it's quite costly. And I think that's one of the things that's sort of holding back geothermal from becoming a more viable energy source. I mean, the energy is there, it's just very costly. A lot of these reservoirs are quite deep. So we're drilling a lot deeper than we're used to drilling in, say, oil and gas. And so the deeper we drill, the more expensive it will be. So a lot of the more commercial geothermal um, applications would be government funded. So Evor is a company based in Calgary, but they've got one of the largest sort of closed loop geothermal operations that they're undertaking in Germany, which they get a lot of funding from the German government there, and that's why they've been able to undertake it. For the cost between these ones, I would say conventional geothermal is the least expensive because it's just drilling wells that are not connected to each other. We're not using any advanced drilling technology to connect them in those U-shape or closed loops. We're not hydraulically fracturing, so those would be the least cost effective. But those tend to be in reservoirs where maybe the temperature is a lot lower, so the amount of energy that we can get from them might not be as efficient. It depends on which company you talk to about which method is going to be the most scalable. Because the good thing about closed loop geothermal is that it can be used in any type of reservoir, so that lends itself to scalability. It's just quite costly, and so that's why EGS is quite popular in the United States right now, being looked at.
Okay, well, thank you. Let me open the floor to questions. Bill Richards?
Hi, thanks, Claudia. Thanks, Kevin. That was great. I'm interested in carbon storage in saline aquifers at the regional scale, moving into the next phase where we're not mucking around with just a couple of wells in a few kilometers, but we're seriously looking at maybe putting in 100 wells on a continental margin at 500,000 tons a year each. With the big worry there not being near wellbore effects, but pressure space at the regional scale. I was wondering if you could comment on whether you guys have done any work at that scale or have thought about it, and how effective the software you have would be at working at those sort of scales.
Yeah, that's a great question. So we have looked at much larger scales, like even when it comes to fewer wells, when these companies are making applications to the government, we need to model quite a large area. So we're not just looking at localized around the wellbore, but a fairly large region. What happens when we're injecting is that the plume might be contained around the well or to a certain distance, but the pressure will propagate a lot faster than the plume because the water is fairly incompressible. So we have looked at fairly large scale models, hundreds of kilometers or well, tens and hundreds of kilometers in each direction away from the injection source. Particularly if there's concerns that it's going to interact with some other operation. Because usually when companies are making applications, they have their lease area, but that lease area is not the boundary of the reservoir. That reservoir might be in contact with either another storage site or even potentially like a gas reservoir. And so we want to make sure that we can model the pressure propagation between where they're injecting and then where they're producing. So yeah, we've modeled that and looked at large scale operations before.
Thanks. Yeah, that's exactly where I was wondering about with the interference between projects. Just a follow-up question. Given that the water is incompressible, if you do have an exit point from the system, from the aquifer system, and say into a lake or into the seabed, through some pock marks or some fluid evacuation features, has there been much thought into how the environmental people might react to that. I know you're only displacing connate water into a freshwater system, but you never, in the literature, you never see people worrying about that. But if we do CO2 storage at a large scale, that seems to me is inevitably going to happen.
Yeah, like usually in the studies that we've worked on is even if there is some sort of like underground river or like if it's open to the atmosphere with a lake, we'll model the impact that it might have on the storage operation. But we've usually mostly focused on if the CO2 is getting there. So like where is the CO2 being contained? But we would have the ability to recognize, okay, even if the CO2 is contained, how much water is being pushed into these areas prior to injecting as well.
Yeah, thanks. I think that's an area that's under researched at the moment. But thanks for your presentation and the answer to the questions.
Thank you,
thanks.
Bill. Thank you, Kevin. I have a hand here, Armugan. I guess he's online question. Go ahead, Armugan.
Thank you, Claudio. Kevin, one quick question. When it comes to the practical reality of enhanced geothermal systems, is it possible to use this technology to enhance the geothermal gradient to an ideal 25 degrees Celsius to 30 degrees Celsius per kilometer? Let's say if we are talking about Canadian North, let's say Inuvik, and if the geothermal gradient for a specific location is, let's say, 15 degrees Celsius per kilometer, can we use enhanced geothermal system technology to actually bring the temperature higher to an ideal 25 to 30 degrees Celsius per kilometer of range?
I mean, we can't necessarily change the geothermal gradient in the reservoir, but we can change or optimize how much heat we extract from it. And one technology that we looked at in EGS is they were injecting the fractures, or so they created these fractures, but then they injected a substance that sort of increased the conductivity. And I don't remember exactly what they were injecting, but so a typical fracture, we would inject water and then we would inject some sand or some sort of proppant to keep the fracture open. But they were injecting or were considering injecting another material that would sort of act as a enhanced conduction, so that instead of just getting heat from sort of like it would increase the heat conduction, and they were actually not flowing the fluid through those fractures. It was just the heat that was being conducted. So that was one thing that I've seen, but I don't recall the exact details of that one. Yeah, I guess that's one potential way that EGS could be used.
Okay. Thank you, Kevin. One last question because we have run out of time. There's a question here on the chat. I'm going to read it. Not sure whether you can read it yourself. Regarding the geomechanical simulation discussed, was any software like TOF used for coupling, were all fluid flow and caprock integrity assessment performed just in the CMG? Very technical.
Okay, so yeah, so in the example shown, it's all through CMG, because in CMG we can model the reservoir as well as the caprock. So these models were taken from the surface all the way down into the actual geothermal reservoir, and we were modeling the wellbore. So we have the dynamic wellbore that we've included. We're modeling the caprock and any earth up to surface, and then we're also modeling where the fluid flow is happening as well. So that's all taken care of in CMG, and then we've done a comparison to other geothermal softwares, including TUF2. We did a comparison and we're able to match the results with TUF2.
Okay, well, thank you very much, Kevin. Don't see any more questions. Thanks for your presentation. Greatly appreciated. It ran a bit longer, but was quite interesting. Thanks again for agreeing to deliver this presentation. A pleasure hosting you virtually. Hopefully we'll have a chance to meet in person in the future. Thanks, Kevin. I appreciate it.
Yeah, thank you so much. Thanks for inviting me and allowing me to present. It's been great.
Our pleasure. Thank you. Bye for now.